Hi guys, we're going to have a look at some vector proofs today. I'm going to do this in two parts for you. Part one is going to be the rigorous, pretty meaty stuff about how to actually do rigorous proofs of geometrical facts and theorems, which will not appear on the exam, I can assure you, but they're great for confidence building, for knowledge, just for basically getting your head around how to do vectors. For that, they're absolutely unbeatable. But they won't be on the exam. Only much simpler stuff's on the exam. In part two of this series on vector proofs, I'm going to give you actually a vector proof which I've seen on an exam, and more typical kind of questions that they ask you, which are easier for them to set. Because the problem with the vector proofs is that they would be incredibly difficult to correct. Really incredibly difficult. So they give you simple stuff and then they put the more knotty concepts in multiple choice questions. So I'll give you a few of those in part two. Okay? Right, let's go and have a look at some of this stuff. Alright, so vector proofs can be used to prove geometrical theorems and facts, which I just stated before. And the following vector facts and interpretations can be used, and I recommend that they are. Parallel lines. So if their vectors are parallel, then you're going to have vector A is k times vector B. In other words, it's a scalar multiple. You know that, but you have to use that fact. Perpendicular lines, yes, the dot product will equal 0 because they will be at 90 degrees to each other, and cos of 90 degrees equals 0. Third thing is side length squared. If you've got any theorems with like Pythagoras' theorem, for example, where you've got a squared equals b squared plus c squared, in a vectorish kind of way, that really means the dot product of a vector with itself, and that's how you manipulate your way around to getting that concept. Yep. Okay, we'll do that in a minute. This one here, collinear points. Now that's something which students just don't know what that means. It basically means that the points are on the same straight line. So I've showed you there that if A, B, and C are they would be A, B, and C are collinear if vector AB is parallel to BC and B is the point in common to both at the end of one and at the beginning of the one that it joins with, right? So if they are parallel and B is the common point in the middle, then yes, they are collinear. They have to be on the same straight line. That makes sense, doesn't it? Yeah. Concentric lines. Now that means, concentric means they all pass through the same point, okay? That's what that means. Now, I've drawn you a little diagram here with that concept. That's a triangle, and it happens that the medians of a triangle are concentric. So that means, as I've said there, for the medians of A, B, C, vectors A, D, B, E, and E, F are concentric at G. And yes. So after finding the intersection point of, say, A, D, what is that, A, D, yes, that's that one, A, D, and B, E, then what you would, what have I said there? Then vector C, G, and G, F would be, oh yeah, then what you would do to prove the three medians are concentric, after you've proved that, say, A, D, well, you just make an intersection point of A, B, and D, E, B, E, I mean, A, D, and B, E. Then what you would do is you'd take this vector F, G, and this vector G, C, and prove that they were parallel. That would prove that that third line is a median because it's a straight line going through G also. Get it? Yeah, okay. So that's what you do. Now here's a hot tip for you. Please use all of the information which characterises the geometric shape that's being used in the vector proof. You have to use every single thing about that shape that makes it the way it is if you want to be able to prove the vector proof. And that's just a fact of maths anyway, you know, that you're always using the information they give you to work up to the end result. The other thing is you adapt the known geometric characteristics into a vector equivalent form in the proof, such as what I said above where I was saying a squared, length of a squared equals a dot a for a vector. That's how you do a squared, side a squared in vector format. You just do a dot a. And the last thing is, which seems pretty obvious, but some students just get into such a mess with these vector proofs, it's an NB for you. please don't start off by assuming the thing you're trying to prove, because that doesn't prove anything. Okay, you can't start off assuming the thing you're trying to prove. Okay, and it might sound obvious, but you'd be surprised the number of people that get into a big tangle and they start by assuming what they're trying to prove, which gets you into nothing but a circular argument and a big mess. Right. Yes, here's an NB for you. I'm just putting a disclaimer here for you just to let you off the hook a bit and make you feel a bit more relaxed. The following examples I'm giving you are for practice and development of understanding and confidence only. They are elaborate proofs and they're extremely unlikely to end up being appearing in exams, right? So don't worry about it. So just relax and enjoy the following pages, which I'm going to share with you. Got 3 or 4 proofs here, and they're absolutely fantastic fun when you get the hang of how to do them. But a lot of students find them very hard, which is why it's a good thing that they don't actually appear on the exams as hard questions. Alright, we're going to prove Pythagoras' theorem with vectors. Now this is really a blast, guys. Watch this. Here's a right angle triangle ABC for you and me, and I'm going to make them into vectors, right? So I've put the arrowheads there. You see I've got vector A there, I've got vector B with its arrowhead there, and I've got vector C going up that way, and I've got the right angle. Now you'll notice the very first thing about this, guys, I'm setting myself up. So A is the hypotenuse, so A squared is going to be B squared plus C squared. You see that? And another thing that you'll notice here is that I've set this up so that the right angle is the tail of vector B and vector C, such that if I get a B dot C, which I can tell you in advance I'm going to get, you'll know that you've set that up correctly, so that the scalar or dot product of B dot C will be 0. It's not so critically important you do that, but it's just good form. Okay, it's just good form. Okay, so here we go. To prove that A squared equals B squared plus C squared, written in a vectorish manner, as you'll see, the magnitude of vector A squared equals magnitude of vector B squared plus magnitude of vector C squared. Let's see what I have written for you. The strategy will be, here comes the strategy, guys. Okay, I'm going to use the fact that magnitude of vector A squared will be A dot A, magnitude of vector B all squared will be B dot B, and magnitude of C all squared will be C dot C. That's what I'm doing. I'm turning it around into a vector kind of perspective, right? Yes, and I'm going to try to prove that the left-hand side of this expression up here, that is A magnitude of vector A all squared, equals the right-hand side, which is this magnitude of B all squared plus magnitude of C all squared, using the fact that ABC is a right-angled triangle, because after all it doesn't apply unless it's a right-angled triangle. So that the fact that it's a right-angled triangle has to feature in the proof, guys, doesn't it? It does. Right, so I'm going to start off with a left-hand side expressing A in terms of B and C, because you can see, look, this is A squared in terms of B squared and C squared. So it stands to reason, if I'm going to do A dot A as my starting point here for A squared, it would be a jolly good, very good idea to express A in terms of B and C, and then dot that compound expression of B and C with itself and see where I end up. That's the strategy that you get used to using with these kind of things, yeah? That's what you do, and you wait till you see what happens. They're really, really great fun. Well, I find them great fun. Hopefully you will too after you do a few. But, you know, they won't come easily at first. Okay, the left-hand side of that star equation is a magnitude vector A all squared, isn't it? Yes. Which is A dot A, as I explained to you, vector A dot A. Now, from the triangle ABC, I can say that the way I've drawn the vectors, and you can draw them any way you like, it doesn't matter, with the arrows, whichever way you like, it really doesn't matter in the end. Okay, so I'm saying there that a vector A, what is it equal to? Just follow from tail to nose of vector A would be minus C plus B. That's right, wouldn't it? So therefore the next line is going to be, left-hand side is A dotted with A, so therefore I'll write that in a compound way in terms of B and C and dot them and bombs away and see what happens. Yep. Okay, expanding that out. Yeah, it's very interesting. So that's going to be, next line, It's going to be magnitude of B all squared plus magnitude of C all squared, because that's what B dot B and C dot C are respectively, minus 2 times B dot C. That's pretty interesting. Now, do you know what we've just done? Do you know what we just did? Well, we've just proved the cosine rule. We have. Isn't that something? You look at it, because 2b dot c is 2 times magnitude of b times magnitude of c times cos of the angle between them. And that is exactly a statement of the cosine rule you're looking at there with your beady eyes in great awe and wonderment. So, now before I get too carried away with all this palaver, what have I said there? I'm just explaining that magnitude of b, vector b squared is b dot b, and magnitude of c vector all squared is c dot c. That's basically how I got from that line down to that line, okay? So yes, as I've written here for you, this is the cosine rule. It is indeed. But now we're going to take this a step further, because if angle BAC, in other words, this angle here, is a right angle, oh my goodness, guess what the cosine rule becomes? Yes, because in triangle ABC is right angled, and B is perpendicular, vector B is perpendicular to vector C, then that last term down here, guys, is going to vanish. It's going to disappear off into the vector ether. Yes? And we're going to be left with, that. And therefore we get the right-hand side is that, which is exactly Pythagoras' theorem. Isn't it beautiful? So therefore you've got vector A magnitude all squared equals vector B magnitude all squared plus vector C magnitude all squared as required. Isn't it great? We've just done, in one fell swoop, we've proved the cosine rule, and for the special case of a right angle triangle, we've proved it becomes Pythagoras' theorem. Oh gee, if he was only here today to see this, eh? Yes, I know I'm insane, but I enjoy it. Now, we have to prove that in a circle, the angle subtended by the diameter at the circumference is a right angle. Well, a mighty fine proof too. Here's our little diagram, and we're going to prove that angle ACB is 90 degrees. Well, it's pretty easy to prove, actually. Here's our strategy. Now, what I'm going to try and do is I'm going to try and prove that a vector CA dotted with vector CB is 0. That's how you prove 90 degrees in any vector proof. Yep? Good. Now, I'm going to use, now this is the bottom line with these proofs, guys. What am I going to use? Well, in answer to that question to myself, I'm going to use all the information that I can in this situation. So I'm going to have to use the fact that that angle has been subtended to the circumference. In other words, C is on the circumference. I also have to use the fact that A and B are on the circumference, and in fact that they go through the centre of the circle. In other words, they form a diameter. Yes? I have to use all that information in a vectorish manner, mathematically notated, for the proof to pop out the other end, right? That's what you've got to do. So, what I'm saying is all the information relevant to this circle theorem is got to be used in the proof. That is, that AO equals OB, now expressed in a vector way, okay? A to O would have to be the same as O to B, not B to O, because they've got to be pointing the same way to be vectors, right? So A to O is the same as O to B. They're circle radii, and C is got to be well and truly nailed in this proof as being on the circumference. Now you might ask, well, how on earth are we supposed to do that? Fear not, my children, I will show you, okay? Because I've done a few of these, and I really find them to be fun. Yes, I know, I need help. Here's the method. Okay, so we basically need to prove that, and I've put arrowheads on them for you here, vector CA dotted with vector CB equals 0. That's all I've got to do, guys. If I can do that, I'm laughing, right? Now, what have I written there? A big mouthful. But I've also got to prove that, but also to incorporate the fact, yes, that C is on the circumference and that AB is the diameter. Yes, I've got to do that. This can be achieved, ladies and gentlemen, by putting another radius, I put that in quotes, because it's not the same vector as radius A to O and O to B, but another quote unquote radius vector line in as O to C, and I'm going to call that B. I can't call it the same as R as I've written over there for A to O and O to B, because it is not R. It might be the same length, but it's not the same direction. Okay, so refer diagram. Are you watching? Here it comes. Kaboom! Right now, if you put that line in there. Now, the beautiful part about that is I can easily then wangle this description of C over to A so that I can dot it with C over to B. I can wangle it and express that vector C to A in a pathway which incorporates this information, this B thing, this R thing, and from C to B I can go incorporating it this way, this B thing and this R thing. And guess what I'm going to do? I'm going to dot them. And you can bet your bottom dollar, guys, that the fact that B is the same length as R has to come out somewhere in the proof. Otherwise it won't be proved, okay? Yeah, because that it nails the fact that C is on the circumference. Isn't it beautiful? Anyway, I think it is. So let's keep going with this. Yeah, what have I said there? And then define. Have I said it's? And then defining. Yeah. Define CA and CB in terms of B and C. That's what I've done. Yeah, that's what I've done. Right. Let's get going. Now, here's my method. So I'm saying let's define C to A. It's, if you follow along, it's going to be, here's the tail, minus B minus R, the way I've drawn it, right? You can draw it your own way, but as long as you're consistent, it'll work for you, right? Now the next bit, C to B, by the same process, will be minus B plus R. Now I'm going to dot them together, and you watch with wonder at what occurs. Okay, multiply all that stuff out, and let's see what we get. B dot B minus B dot R plus B dot R. Be careful with all the pluses and minuses. Minus R dot R. Now, instantly I can see those two middle terms are going to go bye-byes. They're cancelling, right, because they're the same as each other. Now, look what I've got left here, guys. Just look. I've got B, magnitude of B squared minus magnitude of R squared. And I told you, didn't I? That's as far as you get, unless you also incorporate into the proof the fact that the magnitude of B is the same as the magnitude of R because they're both radii of the circle. And that's how it comes. That's how you work it out. Okay, so yeah, because they're both radii of the circle. And so therefore, CA dotted with CB is B squared minus R squared, which is going to be, because they're both the same length, that equals 0. So therefore, what I'm saying is, because neither B nor R are 0 vectors, the only way that you can get the dot product equal to 0 is if the angle between them is 90 degrees. Okay, so I've proved it, guys, and I'm laughing, and hope you are too. So therefore, yeah, angle ACB is 90 degrees as required. Isn't it great? Vector proofs are very, very interesting. Without any further ado, we'll do the next one. So what have I got to prove now? That the diagonals of a rhombus, okay, do you know what a rhombus is? I hope. It's a squashed square, okay? Parallelogram, which used to be a square, okay? It's over on a slant. So the diagonals of a rhombus bisect each other at right angles, right? Here comes your diagram. A, B, C, D. And by the way, do you know that you have to, if you're labelling a four-sided figure like that, you must label around the periphery like that. Don't go A, B, C, D. That's wrong, because you wouldn't end up with the right shape without taking your pen off the page. You've got to be able to do it without taking your pen off the page, from A to B to C to D, and getting the right shape, yeah? Okay, so what have I drawn there for you? I've drawn all the information that I can think of for a rhombus. In other words, AB is parallel to, oh, I haven't drawn it, but it is parallel to DC. Yeah, it's a parallelogram, and I've also, the opposite sides are parallel, and the other bit of vital information is that this side length here equals that side length there, which changes it from just a common or garden parallelogram to a rhombus, which is a special case where adjacent sides are equal in length. Yeah. Now let's just have a look at how we're going to try and do this. To prove, we've got to try and prove that A vector A to O. What's that? Oh yeah, that's a part of the diagonal. A to O is equal to O to C. We also got to prove that D to O, magnitudes, these are magnitudes, guys, that vector D, magnitude of vector D to O is the same as magnitude of O to B. Now that will prove that the diagonals have bisected each other, right? Yeah, and if we also prove that vector O to A, which is half of that diagonal, dotted with vector O to D, is naught, then we've actually proved that they're also at right angles to each other, which is all we need to do to prove what they're asking us to prove, right? Now, I'm not suggesting for a moment that these diagonals are the same length. In fact, they're not the same length, but they do bisect each other. So that's the bit we've got to prove, that the halves are actually halves for both of the diagonals, yeah? And O is actually at the centre of each diagonal. Okay, so what's my strategy going to be? Well, now this is a really, really great strategy for proving these kind of things. We're proving something's bisecting each other or whatever. What you do, I've learned the easy way to do this over the years. What you do is you assume, you make an assumption. You say, I'm going to let O be the midpoint of AC. That's it. I'm going to say, yes, Mr. O, you are, by my assumption, the midpoint of AC, or the other one, BD, it doesn't matter, but just one of them, right? Then if you can also prove that O is the midpoint of DB with a vector method, then you've proved that they do in fact bisect each other. So you assume the one, and then you prove that the other one is also the midpoint of the other one, if you know what I mean, that O is the midpoint of the other one that you haven't originally assumed it's the midpoint of. It's really easy to do, actually, too. And you watch it, you'll really like it. So, what have I said here? This is proven, yeah, that bit's proven that O is the midpoint of DB if BO, vector BO, equals vector OD. It's proven, and that's all I've got to do. And then I've got to find the dot product of OA and OD, yeah, and prove it equals to 0. Now, if I do that, then I've proved that the diagonals are at right angles to each other, and everything's good. Do you agree with my strategy? Yeah, assume that O is the midpoint of AC, then prove that O is also the midpoint of DB, right? Midpoint of DB. And that will mean that if vector BO equals OD, then not only are they pointing parallel, but they're equal, which means O's got to be in the middle of a straight line. That's what we're saying. Now, does that make sense? Hope so. Now, what are we going to use? We're going to use the fact that vector AB equals vector DC. They're opposite sides. We're going to prove that vector BC equals vector AD. They're opposite parallel sides. And we're also going to prove that the magnitude of little a, which is A, capital B, is equal to the magnitude of vector little b, which I've written as capital B to capital C. That's all I've got to do. And it's really easy. Let's go. Here's the method. So I'm saying that AC, that's the diagonal from bottom left to top right, equals little a plus little b. I'm working my way around here to do this. Now, that's it, that's the crucial bit. Let O be the midpoint of AC, diagonal AC, right? So, therefore, what I'm saying is that AO equals OC, which would be half of that combined vector, because AC would be, as I've said above, 2 lines above, is A plus B. So AO equals OC equals half of A plus B by my definition. I've set it up that way. I'm allowed to assume that, because that's what I've set it up that way. Now I've got to prove that O is the midpoint of BD, right? Okay, now, BO, here we go. I'm going to say that's equal, in a roundabout way, in terms of stuff that I already understand, is B to A plus A to O. So here it is, B to A plus A to O, isn't it? Now let's just work that out. B to A is minus A, isn't it? Going against the grain of AB. And A to O is half of vector AC. Yeah, now let's simplify that. What do we get? Very nice. Now, if I can also prove, ladies and gentlemen, that OD is the same as that, then I've proved that O is the midpoint of the straight line BD. That's what I've proved. Alright? So, here we go. OD, now how am I doing that? I'm going OD, okay, I'll go from O to A, because this is along the diagonal which I've set up so that O is the midpoint of it. So it's O to A plus A to D, isn't it? Yeah, good. So that's what you get for O to A is minus A to O. Yeah, that's why the minus sign's out the front, plus vector B, which is AD. And now let's just simplify that, and you watch. Oh, goody. Isn't that great? Look, they're the same. They're the same. BO is the same as OD. So I've now proved, ladies and gentlemen, those two diagonals bisect each other. Absolutely proven, rock solid. Yes, so BO is OD, that is the dissect. Yes, so therefore BD is a diagonal, and yes, it's bisected at O, because it's a straight line, and O is the midpoint. Now all we've got to do now is do the dot product of the diagonals, and we're done. So here we go, AO and OD. Now, yeah, that's right. Yeah, that's the. Wait a minute, AO to OD. Yeah, well, I've done that over there, haven't I? Yeah, AO is that. Yeah, and OD is that little beastie, right? So let's just multiply this out and see what we get. And I'm sure we're going to get 0. Otherwise, I'm in serious trouble. Right, I've taken the quarter out the front, the half times a half, and I've just multiplied them out. Now, where's the cancelling going to happen, ladies and gentlemen? Where's the cancelling going to happen? Now, I just spotted it. So I'm saying to you, ladies and gentlemen, the only thing we haven't used in this proof yet is the fact that the magnitude of A is the same as little a, vector little a is the same as the magnitude of vector little b. We haven't used that yet, and we are going to have to use that in the proof, because that's one of the characteristics of a rhombus, which has not been incorporated into the proof yet. So, right, so what's cancelling? The middle terms, goodbye, goodbye. And yeah, so what we got here is a quarter of magnitude of b squared minus magnitude of a squared, and amazingly we know that those two things are the same because adjacent sides in a rhombus are equal. So that comes out to be, yeah, that's right. So therefore that comes out to be 0. Hence, ladies and gentlemen, the diagonals are perpendicular, and we've proven everything we need to prove. Okay, we've done it. There it is. Both things are proven. Yes, I know. It's mighty fun, isn't it? It's awesome, actually, using vectors to prove all these amazing geometrical thingies. Now, the last one, I'll just hurry that up a bit. Prove. Now, this is the kingpin one here. You'd never get this anywhere within 100 kilometres of an exam, so don't worry about it. But it's a very interesting situation, and I want to show you just to help you gain confidence in what we're doing here, because I want you to go and have a go at these proofs yourself after we're finished here. So what I'm asking what I'm asking myself to prove here is to prove that the medians, that is the line from the vertex to the midpoint of the opposite side, medians of a triangle are concentric, that is, they all go through the same point, and that they are divided into lengths in the ratio of 1:2 by this point of intersection of the medians. Now, okay, yes, it's clear as mud. Look, I'll do a diagram. You'll see. You will see. There's the triangle, and I've shown, yeah, so I'm showing midpoints there, aren't I? Yeah, and you can see that point G is the point that all the medians go through. So there it is. Now, what have I got to prove? I've got to prove, one, that G is the intersection point of the three medians, that is AD, BE, and CF. That's the first thing I've got to prove. And the second thing I've got to prove is this ratio of the parts of those of those medians which are cut in two by point G, if you like. So I've got to prove that the ratios of length, say CG to GF, what's that? CG to GF is 2:1, yeah? And similarly that AG to GD is 2:1, and similarly that BG to GE is 2:1. Yeah, I know, gasp. How do you do that? Well, it's actually very, very simple. So the strategy is I'm going to basically define some pronumerals here, because I can't do anything unless I do that. So I'm going to say let CG be K times CF, where K will be a fraction. right? And we're hoping it'll be 2/3, right? Because if that's divided into the ratio 2:1, that's 2 parts out of 3, which would be 2/3, yeah? We're also going to say that BG equal L times BE. Same thing, hoping that L will be 2/3, yeah? Get that? We're going to let AB equal little a, so that's AC equal little b. I know we're getting pronumerals everywhere here. Don't panic, it's alright. I'll put the arrowheads in there and there. Now I've put an M here and for the fraction that AG is of AD, but actually we're not going to need that. So don't worry about the M, just forget it, okay? Now, right, what else have I got here? It's cooked up for you. I'm going to let G equal the... Oh, yes, this is the assumption that I'm going to use. This is, again, this works like the rhombus diagonal thing. So I'm going to let G be the actual point of intersection of two of the medians. And they are this vertical one here, C to F, and B to E. And then, so I'm assuming that point there is the joining point of the two medians that I've just enunciated, and then what I'm going to then prove is that this third thing over here from A to G to D is actually a straight line. Going. So in other words, if I can prove that vector AG is parallel to vector GD, seeing that they share the common point G, then that would prove that that is a median, because this is D is already known to be the midpoint of that line there. So if I can prove to you that vector AG is parallel or a scalar multiple of vector GD, then not only are they parallel, they share the common point G, therefore they are the same straight line, therefore that third line A to G to D, or that would be a straight line median. That's what I'm going to do, yeah? Now, I'm going to form two vector, what I'm going to do, my strategy is I'm going to form two vector pathways for C to G, from C to G. Now, what I'm saying is there. I've already got one here. I can say, well, C to G is K times C to F, isn't it? That's the way I've defined it. But I can also then form another path. I could go around this away, from C to E to G, or I could choose to go around this away, from C to D to G, and all I've got to do is involve another pronumeral, and that's pretty easy to do. So that what I'll do is I'll get two vector pathways from C to G. One of them will involve K, and this one here I think I'll do. This one here would involve L. So once I get two equations for the vector from C to G via different pathways, both involving K and L, I will get two simultaneous equations cooked up, which I can use to then solve for K and L, and hopefully they'll come out to be 2/3 each of them. If they don't, we're back to the drawing board. Now that's my strategy, right? Now that is my strategy. Once I do that, then I've got to prove that, as I said, that AG is parallel to GD. This will prove that all three medians pass through G, because the line AG will be straight and therefore will also be a median. And the last but not least, this bit here, this M thing, this scalar multiple, connecting AG, and D, I've got to prove that that's also ratio 2:1, that M is 2/3, guys. I've got to prove that, otherwise I haven't proved that all three medians are split up in the ratio 2:1 by the point G, have I? So this scalar multiple connecting AG and D to M should prove to be 2/3 once I get the ratio, once I prove that this AG is parallel to GD in the previous step, okay? I should get a scalar multiple of AG compared to GD, and hopefully that'll give me the value of M being 2/3, and that's what I'm saying in all this palaver here. Okay, so it should prove to be 2/3. That is the value of M during this step, that previous step, thus proving that all three medians are divided lengthwise in the ratio 2:1 by G. Now, having done that, then I've done everything. Basically, I will have proved that that third median is a median. That's A to G to D, straight line going through G. And I will have proved that this K is 2/3, that L is 2/3, and M is 2/3, which is everything I have to do. Yeah, that's the strategy that is best and easiest to use with these things. Now, if you're feeling overwhelmed right now, don't worry about it. Listen, I was too when I first came across these things. I thought, what the? But, you know, after a bit of practice and a bit of amazement and learning and thinking and letting it rattle around in your head, they just become pretty routine, these things. I can tell you they do. Okay, let's go. Method. Here we go. CF. Now, I'm just getting this all worked out. CF is equal to C to A, that's down the left-hand side, plus A to F, right? I'm just setting things up, guys. That's equal to minus B, according to my definition of the way I've done it, plus a half of A, isn't it? Yes, that's good. Now, C to G. Now, C to G, therefore, would be K times that C to F, wouldn't it? Yes, so I'm going to put that in that form like that. Right, that's C to G. Now, that's the one pathway from C to G, the easy one, the vertical one down, as the way that diagram looks. It looks vertical anyway. It's not deliberately vertical, but it just looks vertical in the way I've drawn it. Now, that's the second pathway is coming up now. Also, CG is equal to CE. Now, I've gone down here, so I can get L involved by zooming down there, right? So it's CE, which happens to be minus a half of B, plus EG, which I'll have to work out what that is. That'll take a bit of doing, but it's all right, no problem. So it's minus a half of B plus EG. Now, what's EG? It's a bit of a chain reaction here, domino effect. So EG is 1 minus L times EB. Oh, goodness, now we've got to work out, that's what I mean, domino effect. Now we've got to work out EB. Well, what's EB? Go from the tail to the head any way you like. Tail being E, head being B. So what have I done? I said it's minus a half of B, that's going from E to A, plus all of A, that's going from A to B. Yeah? Good. Now we better put all this together before we get completely confused. So CG is, I'm already confused, is, well, that's what it comes out to be, right? So it's, oh yeah, I know, I'm with it. It's minus a half B plus EG, which is this thing, and that thing is that thing. So that's all put together in a big consolidated form in that equation there. So therefore, I'm just going to simplify that now before I go completely stark raving mad. And what do I get? Righto, that's good. That's good. Now I'm very happy because I've got L in there. See, and I had K in the very first one that I did over here. So where is it? Where's the K one? There, that one there, right? Yeah, it's got K. This one's going to have L, and we're going to equate them together. That's what we're going to do. Just find whether, and we're going to find out what K and L are on the next screen. There it is. Simplified. Okay? Two different pathways for the same vector. Nifty, eh? Over we go in a minute. There it is. Right, so that's what we had. That's what we had. And I've set them up as two simultaneous equations for you now. You see, look, if C to G equals this amount of A plus this amount of B, and they're both the same, see? This one's also something else times A plus something else times B. Well, then the coefficients must be equal. It's the only way you can do it, guys. The coefficients must be equal, and I can equate them as equal by forming two new equations. So therefore, from equation 1 and 2, I can say that this first coefficient thingy here, where is it? That thing there, that half K thing equals this bit down here on the second from the second equation. All about the thingos times vector A, both of them. This one here is the thingos times the vector B from both those equations equated together. Right? Now, we're just going to work through this now and solve them for K and for L. And, it really is very simple and methodical. Equation 3, I'm calling it, and 4, I'm going to multiply equation 3 by 2, so I can just add those two equations then. That's what I get when I multiply equation 3 by 2, call it equation 3a. Now I'm going to add equation 3a to 4, because the k's will drop out, and I'll just get L. Yeah, good. Now, put the 1 over the other side and multiply both sides by 2/3, and what do I get? Of course I do. Hey, celebrate. That's what I wanted. L is 2/3. So therefore what I'm saying over here is that therefore B to G must be 2/3 of BE. And that's exactly what I want. Now let's keep going and solve it for k. We're going to substitute for L as being 2/3 into equation 3a above, and what do we get? Yes, that's very nice. There it is. So now look, ain't it grand? We've just proved what we have to prove for 2 or 3 out of those, the 2 intersecting medians that we started off with, the vertical one and the one from B to E. Okay, now we've got the ratio of the side thingies, the bits that are divided into 2 bits by G. Now what we've got to do now, guys, is we've just got to prove that A to G to D is a straight line, right, is a straight line by proving that the vectors are parallel to each other, sharing the common point G. Then we've proved that that one's a median as well. And the last bit is whatever the ratio of the length of AG to GD is, hopefully that'll come out to be 2:1, because that means that then AG is 2/3 of AD, if you know what I'm trying to say. Do you? I probably went too fast. But look, it'll all unfold here for you. Okay, here we're going to prove the third median. Oh, geez, this is exciting, isn't it? Better than watching a movie. Yes, I know. I need help. Don't worry. I'm having a good time. So A to G is, now I'm going to go, what am I doing now? I'm saying that's A to C. Yeah, okay. It's right up there, the left-hand side, sloping side, from A to C plus C down vertically to G in that case, right? So I'm getting my A to G. Then I'm going to do the same thing with G to D later, and you watch, because I now know the values of K and L. Therefore, I won't have pronumerals all over the place anymore, because I can assume they're 2/3 because I've proved it, right? So let's go for this. So what's that? That's B plus 2/3. See, I'm using that nice little 2/3 there. That's my little prize from the previous bit. 2/3 of C to F. Yes, and C to F is just going to be simply, what's that? Come on, we'll work it out just for looking at the diagram. C to F would be minus B plus half of A, wouldn't it? Oh, I think so. Very excellent. Now we'll see there's no pronumerals in there anywhere, just B's and A's, which is what we want, guys. So what'll it come out to be? Looks like it's 1/3 of B plus 1/3 of A. Good. Now we're going to do the same thing for G to D, right? So I'd suggest what we should do there is also G to D. We're going to go upwards from G to C and then down the right-hand side halfway to point D, yeah? And we know the value of K. Again, we know the value of K, so there's going to be no K's and L's or anything like that to worry us. So that's minus 2/3. Now you notice I've got the minus 2/3 there because I'm going in the opposite direction to C to F, right? So I'm going from G to C, right, against the grain of what I previously defined C to F was. So it's minus 2/3. Is that right? Yeah, minus 2/3 of that C to F vector, plus C to D, which I worked out. When did I work that out before? C to D. C to D. So it's half of. Oh yeah, it's a half of C to B, and C to B is minus B plus A. Yeah, that all makes sense, doesn't it? Now, come on, simplify it, and here is our moment of glory, guys. It's got to be a scalar multiple of AG, otherwise we're down the drain. Oh, look. Oh, no, that's not yet. No. I've got to simplify it a bit more. Yes. Look. It's 1/6 of B plus 1/6 of A. This beast over here is 1/3 of B plus 1/3 of A. So this is exactly twice as much as that, and that's telling me we're on clover, guys. We have got it. We know that they're parallel, and one is double the other, which is exactly what you want for that 2/3 thingy, fraction thingy. AG is twice GD, therefore AG is parallel to GD, which is marvellous. And M must be 2/3. And here comes the final conclusion. We've done everything we needed to do. Therefore, AD is the third median. It's a straight line going through G, and it is divided into the ratio of AG to GD is 2:1 by G as required box time. Thank you, Mr. Box. You like it? Then you can have it. Star time, we've got to get out of here. It was a very long session. I knew it would be long, but it's very important for you to practice these vector proofs to get confident, because it's one of the weakest areas of all for students. Okay, now part 2, stay tuned, it'll be good. See you later.